This is actually the last lesson from Unit 7 of Geometry. We're kind of at a little bit of a transition point in this course a little bit. We've kind of hit some review of some kind of middle school concepts with a little bit more depth in some places. And then we've got this lesson, which is review. We'll gotta get into it. It's going to be a little bit. This is going to be a little bit different lesson than typically for me. And you'll see why in a minute. Then after this, we're going to kind of move into prepping for trigonometry and prepping for, really it's a lot of prep for physics and a lot of prep for higher math or even arguably video game design and things like that. We're kind of shifting gears, which one of the things that's going to be useful, if you're one of my students anyway, is after this lesson, after this unit, after the test for this unit, we won't have any more proofs. We're kind of moving out of, there's not truly, you'll see as over the course, we're kind of moving out of a logic course and into more of a prep for physics type of class. So let's dive into this lesson and see how it's kind of different. So this is probably my least favorite lesson in all of geometry because unlike pretty much everything else we've done, it's a little bit wibbly wobbly. And what I mean by that is you see words in on this screen like often and assumes, and I thought there was a word usually on here. There's not, but what I mean by wibbly wobbly is there's depending on context, the vocabulary might be a little different. So we're not going to actually do any examples. I'm going to do some kind of pseudo examples and kind of talk through some ideas in a minute. But I want to start by kind of talking about how the word scale versus the word scale factor are often used in math class and whatever. When I teach this concept in pre-algebra, I teach it as when you see scale, it's this, and you have to, and units many times don't match. That we're talking with scale, we're talking about like the scale of a map or things like that. So if you have a map over here with some land masses and some things, and then you've got the real thing over here with the big land masses and whatever, on the map, you might have something like 1 inch equals 500 feet, right? Or whatever, 506 feet apparently, because that's what I ended up writing. So we're talking about stuff like that, where the units often don't match. They can match, and if a problem or a real life situation of some sort says this model or this map has a scale of 30-1 or something like that, then we assume that scale is the units match. Now I'd say, well, if it says 30-1, what are the units? Well, if it's a unitless scale, that's really often in math books, we'll call that the scale factor. And that'll work. That scale factor will work with any units, right? As long as the units match. So whenever it says scale factor, pretty much always the units have to match. And most of the time you'll have a 1 in the numerator or the denominator. Typically, there's the usually. I didn't say usually. I said typically, right? So if you have a 30-1 scale or a 1-30 scale, right, and that'll kind of tell you how big the thing works. Now, so how is this helpful? This is a bunch of like random words and whatever else. And so what I want you to think, and when you're trying to solve these, you want to set up a proportion, right? That's really set up a proportion, right? And that is your goal when you're solving a problem with scale or scale factors. Almost always proportion, or possibly just write a ratio and reduce it, right? So you're going to write a ratio of some sort like a 2 to 10, and then what kind of zero is that? 2 to 10, and then you could reduce that to a 1 to 5 scale or something, right? So you're either going to set up a ratio and reduce it, or you're going to set up a proportion and solve it, right? And that's how you're going to do these problems. So you might have something like where I've got a little model of the Eiffel Tower. That's what this is apparently, right? And a model of the Eiffel Tower, and then I've got the big Eiffel Tower, and then whatever else. And the real Eiffel Tower is, I don't know how tall it is. Do y'all know? I sure don't. 200 feet tall. I don't know. Making stuff up, right? I'm trouble with writing letters. 200 feet tall, and the model I have is 12 inches tall. And then what's the scale, right? Or what's the scale factor, right? And so you'd have to, if you're looking for scale factor, or sometimes, and I actually meant to add to this bit, is that sometimes you will see, like, finding the scale factor is, and this is where we reduce it down to having a 1 in either the numerator or the denominator. We're looking for how many times as large or small or whatever else, as large is this, then that, right? So doing something along those lines, right? So in this kind of pseudo talked through example, if we were trying to find out how many times as large this was, then we'd have to make the units match, right? If we were trying to find the scale of this, we could make a unitless scale, which can be quite useful. And a unitless scale is, again, like I said a minute ago, is often called the scale factor. If you did that, then you'd have to make the units match. But if we were just trying to find the scale, we just do, it's a 12-inch equals 200 feet, right? If we're just trying to find the scale, we can do that, right? And then you'd reduce it by 2, and you'd get 6 over 100, and then reduce that again. So what can we actually reduce by? 4, right? So 4, so we get 3 inches equals 50 feet, right? So you could do that. Or if it asks you how many times as big as this, then we've got to convert our units and make them match. So you'd have to, like, do 50 feet times 12 inches, right? And you'd get 600 feet. No, 600 inches. Inches equals 3 inches. And then we want to reduce it down to give us a 1, to which will give us how. And this, if you're trying to find how many times this is than that, this, how many times as big as is this, like how many times do we have to do it? We want to always turn this into a 1, right? And so we're always going to divide this by this number here, right? So we end up with 1 inch equals 200 inches. So if you were asked in this problem, how many times as big is the real hypothetical Eiffel Tower? It's probably a lot taller than this, honestly. But the real Eiffel Tower, how many times as big? Well, it's 200 times as big. And we're doing problems like that. And the reason why and part of the reason, and we'll see how this works this year in this class. If I need to revisit this lesson in the future, in this lesson video, certainly will, and all of those things. This is like super review. You almost certainly did problems like this in your middle school classes. And so, but those are the kind of things that you're going to be doing. You're going to either be reducing a fraction if you want to do this to that, and if you're doing that, make sure the units match. If you're trying to solve for a missing thing, you're going to set up a proportion, just like we've been doing. That's all there is to it. Y'all do your homework. I'll see you in class. If we need to revisit this one in the future, we certainly can. If not, we're all good. Bye-bye.